You now know a bunch about machine learning. In this video, I'd like to teach you a programming language, Octave, in which you'll be able to very quickly implement the learning algorithms we've seen already and the learning algorithms we'll see later in this course. In the past, I've tried to teach machine learning using a large variety of different programming languages, including C++, Java, Python, NumPy, R, and also Octave. And what I found is that students were able to learn the most productively, learn the most quickly, and prototype your algorithms most quickly using a relatively high-level language like Octave. In fact, what I often see in Silicon Valley is that even if you want to build a large-scale deployment of a learning algorithm, what people will often do is prototype in a language like Octave, which is a great prototyping language, so you can sort of get your learning algorithms working quickly. And then only if you need a very large-scale deployment of it, only then spend your time re-implementing the algorithms in C++ or Java or some other language like that. Because one of the lessons we've learned is that programmer time or developer time, that is your time, the machine learning expert's time, is incredibly valuable. And if you can get your learning algorithms to work more quickly in Octave, then overall you have a huge time savings by first developing the algorithms in Octave and then implementing in like maybe C++ Java only after we have the ideas working. The most common prototyping languages I see people use for machine learning are Octave, MATLAB, Python, NumPy, and R. Octave is nice since it's free open source, and MATLAB works well too, but it's expensive to many people. But if you have access to a copy of MATLAB, you can also use MATLAB for this class. If you know Python NumPy or if you know R, I do see some people use it, but what I see is that people usually end up developing somewhat more slowly in these languages because the Python NumPy syntax is just slightly clunkier than the Octave syntax. And so because of that, and because we're releasing starter code in Octave, I strongly recommend that you not try to do the programming exercises in this class in NumPy or R, but that I do recommend that you instead do the programming exercises for this class in Octave instead. What I'm going to do in this video is go through a list of commands fairly quickly, and the goal is to quickly show you the range of commands and the range of things you could do in Octave. The course website will have a transcript of everything I do, and so after watching this video, you can refer to the transcript posted on the course website when you want to find a command. Concretely, what I recommend you do is first watch the tutorial videos, and after watching to the end, then install Octave on your computer. And finally, go to the course website, download the transcript of the things you see in the session, and type in whatever commands seem interesting to you into Octave, so running on your own computer, so that you can see it work for yourself. And with that, let's get started. Here's my Windows desktop, and I'm going to start up Octave. And I'm now in Octave, and there's my Octave prompt. Let me first show you the elementary operations you can do in Octave. So you type in 5 plus 6, that gives you the answer of 11. 3 minus 2, 5 times 8, 1 over 2, 2 to the power of 6 is 64. So those are the elementary math operations. You can also do logical operations. So 1 equals 2, this evaluates the false. The percent command here is means a comment. So 1 equals 2 evaluates the false, which is represented by 0. 1 not equals to 2. This is true, so that returns 1. Note that the not equal sign is this tilde equals symbol, and not bang equals, which is what some other programming languages use. Let's see, logical operations 1 and 0. Use a double ampersand sign to denote the logical and that evaluates the false, 1 or 0. This is the OR operation, and that evaluates the true. And I can XOR 1 and 0, and that evaluates the 1. This thing over on the left, this octave324.exe:11, this is the default Octave prompt. It shows the version of Octave and so on. If you don't want that prompt, this is somewhat cryptic command, ps quote greater than and so on, that you can use to change the prompt. And I guess this quoted string in the middle, quote greater than space, that's what I prefer my Octave prompt to look like. So if I hit enter, oops, excuse me, like so, PS1, like so. Now my octave prompt has changed to the greater than sign, which, you know, looks quite a bit better. Next, let's talk about octave variables. I can take the variable a and assign it to 3 and hit enter, and now a is equal to 3. If you want to assign a variable but you don't want it to print out the result, if you put a semicolon, the semicolon suppresses the print output. So if I do that, enter, it doesn't print anything, whereas a equals 3, you know, makes it print it out, whereas a equals 3 semicolon doesn't print anything. I can do string assignment, b equals high. Now, if I just enter b, it prints out the variable b. So b is the string high. C equals 3 greater than or equal to 1. So now C evaluates to true. If you want to print out or display a variable, here's how you go about it. Let me set a equals pi. And if I want to print a, I can just type a like so, and I'll print it out. For more complex printing, there's also the disp command, which stands for displays. When I display a, it just prints out a like so. You can also display strings. So disp sprintf, 2 decimals, and %0.2 f, comma a, like so. And this will print out the string 2 decimals colon 3.14. This is kind of a old style C syntax. For those of you that have programmed C before, this is essentially the syntax you use to print strings. So the sprintf generates a string that is this, 2 decimals 3.14 string. This %0.2f means substitute a into here, showing it with 2 digits after the decimal point. And disp takes the string that's generated by the sprintf command, sprintf, or the string printf command, and disp actually displays a string. And to show you another example, sprintf 6 decimals, %0.6f, comma a, and this should print pi with 6 decimal to 6 decimal places. Finally, I was displaying a like so, and it looked like this. You can actually, there are useful shortcuts. You type format long. It causes strings to, by default, be displayed to a lot more decimal places, and format short is a command that restores the default of just printing a small number of digits. Okay, that's how you work with variables. Now let's look at vectors and matrices. Let's say I want to assign A to a matrix. Let me show you an example. 1, 2, semicolon, 3, 4, semicolon, 5, 6. This generates a 3 by 2 matrix A, whose first row is 1, 2, second row is 3, 4, third row is 5, 6. What the semicolon does is essentially say, go to the next row of the matrix. There are other ways to type this in. Type A equals 1, 2, semicolon, 3, 4, semicolon, 5, 6. Like so, and that's another equivalent way of assigning A to be the values of this 3 by 2 matrix. Similarly, you can assign vectors. So V equals 1, 2, 3. This is actually a row vector, or this is a 3 by 1 vector, right? This is a fat Y vector. This is a 1 by 3 matrix, right? Not 3 by 1. If I want to assign this to a column vector, what I would do is instead do V equals 1 semicolon 2 semicolon 3, and this will give me a 3 by 1 instead of 1 by 3 vector. So this gives me a column vector. Here's some more useful notation. I can also set V equals 1 colon 0.1 colon 2. What this does is it sets V to the bunch of elements that start from 1 and increments in steps of 0.1 until you get up to 2. So if I do this, V is going to be this row vector, or this is a 1 by 11 matrix really. That's 1.1, 1.1, 1.2, 1.3, and so on until we get up to 2. Now, I can also set V equals 1 colon 6, and that sets V to be these numbers 1 through 6. Okay. Now, here are some other ways of generating matrices. Ones, 2 by 3, is a command that generates a matrix that is a 2 by 3 matrix that is the matrix of all ones. So if I set C equals 2 times ones, 2 by 3, this generates a 2 by 3 matrix that is all 2's, and this is, you can think of it as a shorter way of writing this, and C equals 222 semicolon 222, which will also give you the same result. Let's set W equals 1's 1 by 3, so this is going to be a row vector, or a row of 3 runs, and similarly you can also set W equals 0's 1 by 3, and this generates a matrix, a 1 by 3 matrix of all zeros. Just a couple more ways to generate matrices. If I do W equals rand 1 by 3, this gives me a 1 by 3 matrix of all random numbers. If I do rand 3 by 3, this gives me a 3 by 3 matrix of all random numbers drawn from the uniform distribution between 0 and 1. So every time I do this, I get a different set of random numbers drawn uniformly between 0 and 1. For those of you that know what a Gaussian random variable is, or for those of you that know what a normal random variable is, you can also set W equals rand n 1 by 3. And so these are going to be 3 values drawn from a Gaussian distribution with mean 0 and variance or standard deviation equal to 1. And you can set more complex things like W equals -6 plus square root 10 times, let's say, rand n 1 by 10,000. And I'm going to put a semicolon at the end because I don't really want this printed out. This is going to be a, it's going to be a vector with 100,000, 10,000 elements. So, well, actually, you know what? Let's print it out. So this will generate a matrix like this, right, with 10,000 elements. So that's what W is. And if I now plot a histogram of W with the hist command, I can now, and Octave's print hist command, it takes a couple seconds to bring this up, but this is a histogram of my random variable for W that was -6 plus square root 10 times this Gaussian random variable. And I can plot a histogram with more buckets, with more bins, with say 50 bins. And this is my histogram of a Gaussian with mean -6, because I have a -6 there, plus square root 10 times this. So the variance of this Gaussian random variable is 10, or the standard deviation is square root of 10, which is about, what, 3.1. Finally, one special command for generating a matrix, which is the I command. So I stands for, this is maybe a pun on the word identity, but so if I set I4, this is the 4 by 4 identity matrix. So set I equals I4, this gives me a 4 by 4 identity matrix, and I equals I6, that gives me a 6 by 6 identity matrix, and I3 is the 3 by 3 identity matrix. Lastly, to wrap up this video, there's one more useful command, which is the help command. So you can type help I, and this brings up the help function for the identity matrix. Hit Q to quit, and you can also type help rand, brings up documentation for the rand, or the random number generation function, or even help, which shows you, help on the help function. So those are the basic operations in Octave, and with this you should be able to generate a few matrices, multiply, add things, and use the basic operations in Octave. In the next video, I'd like to start talking about more sophisticated commands and how to move data around and start to process data in Octave.